Welcome to Ask and Learn.
We're given that a model P of t is equal to 1 over 1 plus a e to the negative kt will tell us the proportion of a population that will know of a rumor at a time t and where a and k are positive constants. What we want to do is first find out when half of the population will have heard of this rumor, and then we also want to determine when is the spread of the rumor at its greatest. And then after that, we want to use that to sketch our function. So this first part here, this means we want it to be 1/2 since P of t will tell us the proportion that we'll know. So we can go ahead and write 1/2 is equal to P of t, which is 1 plus a e to the negative kt all over 1. Then we can go ahead and start trying to solve for t, so we can reciprocate each side of this. And doing that will give us 2 is equal to 1 plus a e to the negative kt. Then we can go ahead and subtract 1 and then divide by a, which is going to give us that 1 over a is equal to e to the negative kt. Then we can take the natural log on each side to cancel out our exponential e and then divide by negative k. So we'll end up with t is equal to the natural log of 1 over a over negative k. Now, something we might recall about natural logs is if we have an exponent, we can go ahead and move that out front. And we just so happen to have that, well, 1 over a is really a to the negative first power, so we can move that exponent out front. So we'd get negative natural log of a all over negative k. Well, these negatives here will cancel out. And we'll get that the natural log of a over k will be when the population, or half of the population, will know. Now, this brings up a point of if a is between 0 and 1, then we get natural log of a is going, natural log of a is going to be negative. And then since k is positive, we'll have a negative number. So an extra restriction outside of a just being positive that we're going to need to add is that a is greater than 1. Because otherwise, this first question doesn't really make any sense for us. So this will actually play a role in part B as well. So it's good that we come to this conclusion now as opposed to later. Right, now, to find when the spread is greatest for our rumor, well, if we were to just take the derivative of p, well, this here tells us the rate. And then if we want to find when the rate is at its largest, that means we need to look for the critical values of the second derivative, or the derivative of our derivative. So this is the derivative that we're going to want to find to be able to find our critical values once we set this equal to 0. So this is what we want to determine. So let's go ahead and first take the derivative of p, and then we can also take the derivative of p of t. So let's go ahead and do this on a new page. So we had that p of t was equal to 1 plus a e to the negative kt all over 1. So remember, this can actually be rewritten as 1 plus a e to the negative kt all to the negative first power. So to take this derivative, we're going to go ahead and use chain rule as well as power rule. So the first derivative is going to be p of t. So we're going to use power rule, -1, 1 plus a e to the negative k t. Now this is going to be to the negative second power, since we subtract 1 off. And then we need to take the derivative of what was on the inside here, so d by dt of 1 plus a e negative kt. And now let's go ahead and start rewriting all this. So this should be -1 over 1 plus a e to the negative kt. And the derivative of what we have in green there should be negative a k e to the negative k t. All right, so let's go ahead and rewrite this a little bit more. So first these negatives cancel out. And then I almost dropped my square right here. Since remember this was -2 for our power. And now something that might help us is if we rewrite this as 1 over e to the kt, this part right here, and expand out our denominator. And it'll just make taking the next derivative a little bit easier. So let's do that. So we're going to have ak all over e to the kt. And now when we do 1 plus a e to the negative kt squared, well, this is going to be 1 plus 2a e to the negative kt plus a squared e to the negative 2kt. And this is just by the perfect square formula. All right. Now let's go ahead and distribute this e to the kt. And doing that is going to give, well, e to the kt plus 2a plus a squared e to the negative kt. And this is all going to be over ak. All right, and now I wanted to write it like this, so we don't have to use the quotient rule or anything else. Because before, if we would have left it like this here, we would have had to either use product rule or quotient rule. Now we can just use essentially what we did before, chain rule, as well as power rule. So let's go ahead and find p double prime of t. So again, remember, this is actually to the negative first power. So we're going to have negative ak e to the kt plus 2a plus, or actually let me just go ahead and write it like we did before, because I might run out of space otherwise. So e to the kt plus 2a plus a squared e to the negative kt, and this will all be squared, and then we have to take the derivative on the inside here. So let me do that in blue. So remember, we're taking the derivative of this because it's chain rule. So the derivative of e to the kt is going to be k e to the kt. The derivative of 2a will just be 0. And then the derivative of a squared e to the negative kt should be negative a squared k e to the negative kt. All right. Now to find our, or actually before we do that, let's go ahead and clean this up a little bit, because we will need to do a little bit of algebra for stuff. So notice that we can factor out a e to the negative kt and a k from these. And I'm also going to distribute this negative into here. So factoring out that k would give us ak squared, and we'd have e to the negative kt. So all over e to the kt plus 2a plus a squared e to the negative kt. And this is all still squared. And then over here we're going to have k, Nope, because we factor that k out. So e to the 2 kt, and then we're going to have minus a squared. But remember, we distributed that negative in, so this should be plus, and let me do this in blue. So this should be plus, and now this should be minus. All right. Now, to find our possible maximum of our first derivative, remember we set the second derivative equal to 0. And so first we know that the denominator will never be able to equal to 0, so we really don't care about that part. And we also know that this part here can also never be equal to 0 because e to the negative kt can never be 0, and a and k are both larger than 0 by assumption. So that means the only thing in this that can actually be negative is this part here. So we really just need to set this equal to 0 to solve for t. So we have negative e 2kt plus a squared is equal to 0. So we can add e to the kt over and then take natural log on each side. So that's going to give us that 2kt is equal to the natural log of a squared. Then we can divide each side by 2k. So we get t is equal to the natural log of a squared over 2k. And then remember earlier we talked about how we can move that out front by one of the log rules. So we get 2 natural log of a over 2k. The 2's cancel out, and we get natural log of a over k. So we're not quite done with this, because we'll still need to use the, so I'm going to say first derivative test in quotes, seeing as we have to use it on the second derivative of our function to see if the first derivative has a maximum. So let's go ahead and zoom out a little bit. That might be a little bit too much. So now what we want to do is find a value that's going to be smaller than this and one that's larger. So we can make a number line. So our critical value here is natural log of a k. And then this here is going to be, remember, our values for p of t, or p double prime of t. So let's go ahead and on the left plug in 0. So let's see what p double prime of 0 is going to be. So p double prime of 0. Well, we can just plug everything in to what we have right here. And doing that, everything should simplify down and give us the following. So ak squared all over 1 plus 2a plus a squared all squared. And then plugging it into that other part, we'll have negative 1 plus a squared. So all of this here we know is going to be bigger than 0, since a and k are both bigger than 0. And we also know this part here is going to be larger than 0, because remember that extra assumption that we made of a being bigger than 1, because otherwise, remember, natural log of ak wouldn't make sense. So over here, we know that to the left of this function is going to be positive, since something larger than 0 and something larger than 0 multiplied together gives us something larger than 0. Now, let's go ahead and plug in a number larger than this one. And let's just go ahead and do just natural log of a. So natural log of a. And so plug in all of this in. Let's see what we end up getting. So it should be ak squared, a to the k, all over actually that should be negative k right there. And then in the denominator, it's going to give us a to the k plus 2a plus a to the negative k. So it should be a squared a to the negative k. And then all of this here is going to be squared. And let me scoot all this over a little bit. And then when we plug this in over here, we'll end up with, so negative a to the 2k plus a squared. And so now, once again, we know that this part here is just going to be strictly larger than 0 since a and k are all positive. And then over here, k is also going to be larger than 1. So then this here has to be larger than 0 also, or less than 0, because we'd have minus a to something larger than 2 plus a squared. So this should be less than 0. So two things multiplied together, positive and negative, will give us negative. So that means the function is increasing, or the first derivative is increasing it to this point and then decreasing after. So that shows that natural log of ak is going to be a max. So I'm going to go ahead and zoom in a little bit. So we have t is equal to natural log of a over k. And this is by the first derivative test on the first derivative. All right, now the last part, they want for us to sketch the graph. So let's just go ahead and do that really quickly. So some things that we might need to know before we sketch this are possibly our intercepts. So let's find out what just p of 0 is going to be. So plugging in p of 0, we'll end up getting 1 over 1 plus a. So I'll just do like 1, 1/2, and then somewhere around here is going to be like 1 over 1 plus a, depending on how large a is. And remember, since we assumed it's larger than 1, it should be below that point. Then we know at 1/2, it'll be natural log of ak, so we can put that point there. And now we need to figure out what the end behavior of this thing is. And if we were to go ahead and take the limit as t approaches infinity of 1 over 1 plus a e to the negative kt to the negative kt. So the only thing that has a t is this part here, and we know that e to the negative kt as t approaches infinity goes to 0. So we'd have a times 0, which is 0, plus 1 is 1. So this limit here is 1, so we know we're going to have a horizontal asymptote at y is equal to 1. So the graph of this function is going to look something kind of like this. So it has to curve up to this point, and then it's going to have to flatten out so we can get closer to this. And actually, if we go and look at our chart over here, remember that the second derivative will tell us that this function should be concave up here since it's positive, and over here it should be negative or concave down to the right of our natural log of A over K. And if we look at this, to the left of it, it definitely looks concave up, and to the right of it, it definitely looks concave down.